Hi, I'm developers. My name is Șerban Constantinescu, and I'm a product manager with Android Platform Security. Today, I will talk to you about the Android memory safety tools, a comprehensive set of tools that can help you improve the quality, maintainability, and security of your codebase. Let's start by taking a look at the agenda. I will talk about the impact of memory bugs in Android. I'll then move on to talk about the tools we have been building over the years, and finish by providing you with a recipe for memory safety. Hopefully, by the end of this talk, you will have a good understanding of the impact such bugs have on your codebase and access to the tools that can help you detect and fix such bugs. So let's start by taking a look at the impact memory bugs have on Android. Every second, we detect over 3,000 crashes associated with memory bugs in the Android ecosystem. Over a month, that accounts to 7.7 billion. More than 1 in 2 apps in Play Store have a native component that's written in C or C++, and therefore might be affected by memory safety bugs. And year upon year, almost since the Android inception, we see that over 60% of the Android vulnerabilities are due to memory safety bugs in our codebase. Therefore, we think it's crucial to reduce the density of such bugs in our codebases. And we think that by doing that, we'll improve the quality. And that's also applicable to platform code, as well as to vendor code and application code. We'll reduce the cost by having a lower number of updates required. And we'll improve the security of our users, which is the most important thing we care about, and a key motivator for our investments in this set of tools. In the recent years, we are seeing that applications are the first line of defense with regard to security. And therefore, fixing memory bugs in widely deployed applications is almost as important as fixing memory bugs in the Android operating system. So as I mentioned, our mission is to reduce the density of memory bugs in our codebases. Here, we're looking at the Android operating system codebase. We're looking at the codebase of vendors that deploy Android devices, but we're also looking at the codebases that application developers are using. For that, we're developing a set of tools that covers C, C++, and unsafe Rust, and is a long-term solution for most code. Also, you might be aware that starting Android 12, we introduced a new platform language that is memory safe, and that being Rust. For now, this is applicable only to platform code, and we see this as a solution for new platform projects. I should mention that the vast majority of the code that is used in Android, it's written in C and C++, and for the foreseeable future, we don't think that those code bases will move to using this new language. Also, for the foreseeable future, we don't intend to extend the support for Rust to application developers. So for now, we encourage you to use the memory safety tools and to work alongside us on reducing the density of memory bugs in the Android code bases. So over the years, we developed a set of tools that span between kernel and user space, and that could be used in development and production. I'll start with KSAN, which is our tool for the kernel development. This has been introduced in Android 7 and is applicable to all 64-bit kernels. KSAN helps developers detect memory safety bugs in the kernel codebase by requiring a recompilation and introducing augmented code that could detect when a memory safety bug is triggered. Similarly, in the user space, we're using hardware ASAN, a tool that has been introduced in Android 10, and it's applicable to all ARM64 targets. However, these tools are currently only used in development, as they introduce a non-significant overhead to the developer, requiring a particular requiring maintaining another build to be used for testing, and also introducing a non-trivial overhead when it comes to performance. In the more recent years, we have been working on a set of tools that can be used in production. These tools probabilistically detect memory safety bugs. So they only are applicable to one in many allocations by adding guard pages and basically detecting use after free, buffer overflows, or buffer underflows. These tools are KFence and GWP-ASAN. GWP-ASAN has been introduced in Android 11 and is available for all targets. And starting Android 12, we're happy to announce that we are extending GWP-ASAN to the kernel through the introduction of KFence. These tools have been a great source of finding memory bugs in the field. But, as I mentioned, because they are probabilistic and don't apply to all allocations, are only addressing part of the vulnerabilities and bugs we're seeing in the Android ecosystem. However, for a number of years now, we have been working closely with ARM on a technology that we think could be a game changer to addressing and fixing memory bugs. The ARM MTE extension will be available on compatible Android 12 devices. And as I mentioned, we see this as a game changer as it could be used in production as well as in development for both kernel and user space, and is applicable to all sorts of allocations, not in a probabilistic manner like KFence or GWP-ASAN. So next, I would like to provide you with a recipe for memory safety. With the tools that I just mentioned, memory safety can become as simple as turning a flag on in your Android build. I will provide you with 4 simple steps that, if followed, can help you reduce and detect bugs in your codebase. As I mentioned, we think that this is fundamental not just to security, but also to the quality of your codebase and to the quality our users observe. First, I will tell you how you enable memory safety tools. Next, I'll talk about the benefits of running our tools on your codebase. Next, I'll talk about finding bugs and how you could use the memory safety bug reports to better address or more quicker address the vulnerabilities and bugs detected. And last but not least, I'll talk about how you can monitor using these tools in production. The first step is to enable memory safety tools. You can do that via an opt-in in the app compat settings or in the Android manifest.xml. No code changes are required. You wouldn't need to rebuild your code base to get a benefit of using these tools. GWP-ASAN has been available since Android 11, and it's available on all devices. To set GWP-ASAN, you would need to set GWP-ASAN mode to always or never. Also, in addition, as I mentioned, on Android 12 devices, we're introducing ARM MTE. So on compatible devices, if you want to use the memory safety tools, you should set memtag mode to off, default, sync, or async. Once you enabled the tools, you should run your code, the same as you would before. As I mentioned, there are no code changes required other than setting these flags. GWP-ASAN only guards a small sample of allocations. When deployed at scale across a large number of devices, this could be extremely helpful, and has helped us over the past releases to detect a number of bugs and faults in the Android codebase. We strongly suggest using GWP-ASAN mode equal always in production, dog food, and continuous integration. For more documentation, follow the link available here. This will take you to our NDK page, where we describe in more detail how you can use GWP-ASAN and what are the benefits of this tool. I should mention that GWP-ASAN works on all hardware starting Android 11. However, GWP-ASAN only covers a small number of allocations. And to be able to more broadly apply the tools to your code base, we encourage developers to use ARM MTE on compatible Android 12 devices. ARM MTE guards all heap allocations. We suggest using memtag mode async for production, as this provides better performance overhead. We also encourage developers to use memtag mode sync in dogfood and continuous integration. Sometimes it might be required to switch between these modes at runtime. For example, when a developer wants to collect the exact stack trace of a particular bug. You can do that using the malloc APIs described at the link provided here. I should further emphasize that you can use the same application on MTE and non-MTE platforms, and that MTE is only available on compatible ARMv9 hardware. At the bottom of this slide, you have a link to a sample application that demonstrates all the modes that I've been talking about and provides you with a sample for how you could use these tools in your code base. Next, I will talk about the bugs that the bug reports our tools provide. In comparison to the regular bug reports, the memory safety tool bug reports also provide a deallocation and allocation stack trace. This is extremely useful when trying to identify why a bug occurs. Over the past year, since the introduction of GWP-ASAN and its deployment at scale, we have seen how useful these tools are. We have detected bugs which have been latent in our code base for many years, and we have previously tried to identify and narrow down the errors that cause those bugs. Getting the allocation and deallocation stack traces has been extremely helpful for that. And as you can see in the hypothetical example provided here, the allocation stack trace that is provided as additional information in these bugs can help you identify what the actual cause of the bug is. Once again, we strongly recommend using these tools in production, in dogfood, continuous integration, and testing. Once used in production, you need to monitor the bugs that are detected in field. GWP-ASAN and MTE generate bug reports via logcat and Thumpzone traces. You can symbolize this exactly as you would normally, and they're also available in the Google Play console. Starting Android 12, we also introduced a new Thumpzone API that could help you extract the Thumpzone on the next app start. We are happy to announce that we've been working with Firebase Crashlytics, and support for our tools will be available via Crashlytics very soon. This is extremely important once your application is deployed in production using the memory safety tools, because an important part of that is monitoring the bugs detected in field. I should also mention that part of our observation is that once used in production, these tools can help you cover a lot more code base, get a lot more code base coverage. You can exercise part of the code base that are otherwise not exercised during testing and CI. And therefore, we think it's extremely important to turn these tools on during production. Next, let's move on to a case study. We have been working closely with Chrome on optimizing and deploying our tools in production. I'm happy to announce that Chrome uses GWP-ASAN in production at scale across the Android ecosystem. And also that Chrome is working on experimenting with MTE. MTE provides performance improvements for certain scanning algorithms that are optimized for finding memory safety bugs. Also, Chrome is taking a look into using MTE to detect bugs on sampled user devices using the sync mode where applicable. With that, I'd also like to mention what Chrome thinks about MTE. You can see here what Parisa thinks about this technology. And that aligns very closely with the Android thoughts on MTE, in that it is a game changer to security, and that it could help us address memory safety bugs in complex pieces of code, a problem that not just our ecosystem faces, but the wider software industry. And we think that ARM-MTE is a very valuable tool for now and for the future. With that, I'd like to thank you for your time. There's a live Q&A session starting now to continue the conversation. To take part, join us on Zoom by clicking the yellow button just below the video player on your sessions page.